Okay, so there are other ways to come up with components. You can make right triangles and think about the signs of the two parts, like this vector would be this vector plus this vector, and then you just do the trigonometry. But one way that always works, and as problems get more complicated, I think is a really good way to do it, and also is a really good way to put it into programs when you're programming stuff like this, is that you can always, so like say this is your angle, okay? If you find the counterclockwise angle from the positive x-axis to this vector, where the vector's tail is at the origin, so if this angle is theta, then you can always just use cosine of theta, sine of theta. Okay, so it's nice if you have something referenced to something else that's referenced to something else. You can just add and subtract counterclockwise and clockwise angles till you get there. So this one, you can think of this as, I'll continue. So here's the negative x. Here's the negative y. So if we're just going to use cosine and sine, you can think of this as like you go all the way around. Let's go all the way around. So this is positive 360 because it's counterclockwise. But then we have to backtrack 70. So minus 70. And so that total counterclockwise angle from the x-axis is positive 290. That distance is 1.5. So this angle, this vector is 1.5 times the cosine of 290, 1.5 times the sine of 290. Any other questions about that one? About the angle stuff? So in like one where, what was that? What was the problem with the 4-meter beam and the pin in the slot joint?
Door is sliding.
Yeah.
Number 19.
19?
Yeah.
Oh, I have it up right here. So let me just talk about that one for a sec, because that's probably, I don't know, that's one of the more complicated ones in this way. Yeah. Okay, so what we're told is that this slot makes an angle of 20 degrees with the vertical. So this angle is 20 degrees. Okay. And one of these questions says, we want a vector with a magnitude of r that's perpendicular to this slot. Okay, so the way I like to, so this has sort of, the slot is referenced to the vertical, and then we're doing something reference to the slot. This is a case where it's easiest to think about it in steps. So let's first come up with a vector that's along the slot, okay? And I'm going to do it, because of the way I have this drawn, the way I have this angle drawn, I'm going to draw my vector parallel to the slot like this, because then you can just immediately see that this angle is 20 degrees. Okay? And now we want a vector that's perpendicular to that. Okay? There's two vectors perpendicular to this black vector. One goes to the upper right and one goes to the lower left. It doesn't matter which one you choose. I'll choose this one. Okay? Since it's perpendicular, we know this angle is 90 degrees. And now let's use that same approach we used in number 12. So from here's the positive x-axis, here's the positive y-axis. So from the positive x-axis, I'm going to go all the way around to here. Okay? So that's a counterclockwise angle of, you can think of that as 270 plus another 20. And it's positive because it's counterclockwise. And now I'm going to go counterclockwise another 90 degrees. Okay, so add all those up. My theta is equal to, what's that? 290, 380. Okay, well, you can use that perfectly fine. You can enter 380 into your calculator. Anything that's over 360, you can subtract 360 and get the same angle. So you could also think of this as 20 degrees. They'll give you the same answer. Okay, that's a really helpful way of thinking about angles that hopefully you'll sort of get used to as the semester goes on. Any other vector questions you'd like me to go over or talk about? Yep.
We still can use sine, cosine, like in...
Yeah. Yes. As long as, I mean, if you're making sense out of it and problems like this are going fine, feel free to use what you're used to using. Yeah. Any other questions? Yep.
If we have like if we learn to do other stuff in a different way in other classes, would you like mark off points?
I won't mark off points, but I do think the ways that I'm telling you, you'll find work pretty well once we start getting into complicated problems. And especially so this is cosine and sine. We only do this stuff in 2D. But in the 3D stuff, the ways that you've learned just aren't going to work, you know. So be sure that you're used to the idea of finding two coordinates, subtracting to find the vector, and then calculating the unit vector in that direction. That you're going to need. Any other questions? Okay. So last time I just had started mentioning separation of variables. So now we're getting into solving ordinary differential equations using separation of variables. I gave it with different variables before, but what variables it is doesn't change the nature of the problem or anything. So I'm going to say, let's say we have this differential equation, dy ds is equal to some function of y times some other function, g of s. Okay, so let's think about what it means to solve this differential equation first. Is this an ordinary or a partial differential equation? This is ordinary because we only have total derivatives. We don't have partial derivatives. What's the independent variable? S, yep. And what is the one, or what are the many dependent variables? Yeah. So that means to solve this means we want to find the function y as a function of s. Okay? And so anytime your differential equation is in a form like this, the way you can solve it is get all the y, like get all the stuff involving the independent variable on one side, get all the stuff involving the dependent variable on the other side, and then integrate both sides. The thing to notice, and I'll do an example right after this, is each time you integrate, so let's say each time you integrate both sides, you get an unknown constant of integration. Well, just to be clear, okay, you're integrating both sides, so you're doing two integrals. You really get two constants of integration, but if you add those up, get them to one side and add them up, it just is the same thing as a single unknown constant of integration. So we're just going to think of that as, we're just going to think of there being a single constant of integration every time you integrate both sides. Okay, we have to solve for that unknown constant of integration using a boundary condition. And so in order to come up with a full solution to this problem, the problem needs to provide one boundary condition, I'll write it as BC, boundary condition, for each integration step. Yes?
Is it usually going to be in the form of initial conditions?
I don't know about usually, sometimes, but you can solve it the same way in any case. So I'll give some examples. The first one I have is an initial condition, but it's just a matter of what the value of the independent variable is, you know. One thing also, how many people in here have taken differential equations? Probably not many. Oh, a lot. Wow. Okay, in differential equations, just to sort of get your bearings on the difference between what we're doing and what you did there, you were often asked to find a general solution, right? So a general solution is all the total solutions where you're not given specific boundary conditions. Okay, in engineering applications, you're pretty much always going to know the boundary conditions. And we're going to, instead of coming up with a general solution, we're going to come up with a solution for that specific set of boundary conditions. So that's the difference between what we want and what mathematicians want. Okay. All right, so first example. So we have this differential equation that says y dot is equal to y squared t squared, where when time is equal to 0, y is equal to 10. Okay, and we want to solve this. Well, maybe the first thing I'll do is expand this into the DDT notation so we can separate variables. So I'm going to write this as dy dt. That's the definition of the dot notation. Remember, dot always means derivative with respect to time. It can't mean derivative with respect to anything else, okay? And this is equal to y squared t squared. And now we have to think about, does this meet the form requirement of using separation of variables? Well, we have a function of y multiplied by a function of t, so this works fine. Okay? And so now I'm just going to get all the y stuff on one side, the t stuff on the other side. So we have dy over y squared is equal to t squared dt. I'll just reformat this. So that's y to the negative 2 dy is equal to t squared dt. And now the only obstacle is whether you're capable of integrating this or not. In this case, it's easy to integrate. So this is negative y to the negative 1 is equal to t cubed over 3 plus c. You can put that constant on whatever side you want, but we get one constant of integration for that one integration of both that we did. And so you could simplify this. What we really want is y as a function of time. We have this relationship here that's pretty close to what we want. We really do have to put it into a format y of t. But let's use the boundary condition now to figure out what this c is. Okay, so I'm going to do that before I simplify it. So now the boundary condition. Well, the boundary condition says that when t is equal to 0, y is equal to 10. Okay, so I'm going to substitute 10 in for y. Zero in for t, and solve for c. So c is equal to negative 0.1. Okay? Any questions about using that boundary condition? So just, you know the value of the dependent variable at a specific value of the independent variable, plug those both into your expression and calculate c. And that's how you do it, whether it's an initial condition where time is equal to 0, or another boundary condition where time is equal to something else. Yes?
So in the answer we want to find c, not the function.
We do want to find the function, so we're almost there now, not quite yet. So now I'm going to update our relationship. And what we have is that negative y to the negative 1 is equal to t cubed over 3 minus 0.1. Okay. And now I just want to find y as a function of time. So I'm going to write this as, I guess I'll write this as 1 over y, multiply both sides by negative 1. And we get negative t cubed over 3 plus, I'll write this as 1 over 10. And now I'll write 1 over y is equal to, get a common denominator here, and you have negative 10t cubed. So the common denominator is 30. So 10t cubed plus 3 over 30. And so now y as a function of time is equal to, I'm just taking the reciprocal of both sides, so 30 over negative 10t cubed plus 3. Any questions about that? So there was a little bit of fiddling, but the only parts, like the differential equation parts, were pretty simple. Everything else is just kind of algebra, just staying with the problem. The differential equations part was, we noticed we could use separation of variables from the form of the differential equation. We separated variables and integrated. And then we used the boundary condition to find the constant of integration. Okay, so here's another example, and this is how it's going to come up most in actual dynamics problems. So let's say that the x component of the velocity is equal to 3t squared plus 5t minus 10. And let's say we know that when time is equal to 0, maybe it is mostly in initial value problems, x is equal to 3. And what we want to do is solve for x as a function of time. Okay, we're trying to find the x component of the position as a function of time. Well, what we know is that the velocity is defined as the total derivative of the position. I'll write that as x, y, z. And so we know that the x component of the velocity is dx dt. Okay, you can think of that also as a definition. So I'm going to rewrite this. And just replace the x component of the velocity with this expression, dx dt. So we have dx dt is equal to 3t squared plus 5t minus 10 where another way of saying this is that x at time equals 0 is equal to 3. Okay, can we put this in the form where we can use separation of variables? I mean, is this in a form where we can use separation of variables? Yeah, basically, think of it like this. The function, so we have to have dx dt is equal to a function of x times a function of y. A function of x times a function of t. Okay? Well, what's the function of t? Perfect. Yep, that whole thing is a function of t. And what's the function of x? 1. Yep. Okay? So we have 1 times this function of t. And so now what we have to do is move the 1 over to the dx side. Well, that's trivial. Move the dt over to this side. And now we can integrate both sides. Integrate dx, you get x. Integrate this stuff and you get t cubed plus 5 halves t squared minus 10t plus the constant. Now what do we need to do? Boundary condition, yep. So use the boundary condition. It says that when t is equal to 0, x is equal to 3. So I'll set this up as 3 is equal to 0 cubed plus 5 halves times 0 squared minus 10 times 0 plus c. And so c is equal to 3. And now that we've found that, we can update, and this puts it in our final form. You know, go back up to this form, just fill in what we know now for c, and we get that x as a function of time is equal to t cubed plus 5 halves t squared minus 10t plus 3. Any questions about that? Well, what do you do in a case like this if you have higher order derivatives? Okay. So what if you have higher order derivatives? Second derivatives, third derivatives. In dynamics, it's pretty unlikely you'd have to deal with more than third order derivatives. So let's say that we know that the acceleration vector of an object is 0, negative g. Let's forget that. Let's just do it as a single. We'll say that the y component of the acceleration is negative g. Okay. Where g is 9.81 meters per second squared. And let's say we want to find y as a function of time, given that the y component of the velocity when time is equal to 0 is v0. And given that the y position when time is equal to 0, we call y0. Yep.
Is the AY equals negative G an equation that we're going to be using a lot of?
Not really, but it's an equation you use a lot in physics 1, you know. And what we're going to do here is just derive the constant acceleration equations, but thinking of it as a separable differential equation. Okay. Okay, well, we're going to do this in 2 steps. We know that the y component of the acceleration is defined as the derivative of the y component of the velocity with respect to time. And so I'll put this in as dvy dt is equal to negative g, where that g isn't a variable, it's just a constant. I could have put in 9.81 instead. Now, is this separable? Yeah, I mean, these are both pretty lame functions. You could think of the function of time is equal to negative g and the function of v is equal to 1, or vice versa. But either way, it's two functions multiplied together. So I can write this as vy is equal to negative g dt dv. That's right. And now you can integrate both sides. I'll pull the constant out of the integral. Okay. And so this says that vy is equal to negative gt plus the constant of integration. And now we'll use the boundary condition to find that c. We can think of this as, let's make this c1, because we're going to have another constant of integration in the next step that isn't necessarily equal to it. Okay, so the boundary condition says we can't use the one with y in it because we don't have any y's yet in our equation, but we can use the first one I gave you. So when time is equal to 0, vy is equal to v0. So I'll put this as v0 is equal to negative g times time is 0 plus c1. And so that tells us that c1 is equal to v0. And now we'll update this. I'm updating this one right before we started the boundary condition. So we have that vy as a function of time is equal to negative gt plus our c1 is now v sub 0. And there's your function. You know, you're used to seeing this function, but that's where it comes from. You know, think of the differential equation that starts with the acceleration being equal to a constant. That's the free fall equation for velocity. But that's not what this problem asked for. It asked for the position, the y position as a function of time. So now we have to do it one more time. So I guess I'll write this as step 2. Now we know that the velocity y component is defined as dy dt. So I'm going to take my updated differential equation here, and I'm going to replace vy with dy dt. And so we get dy dt is equal to negative gt plus v0 to think of the right side here as a function of y times a function of t. You can think of the function of t as negative gt plus v0. Think of the function of y as 1. And so this gives us dy is equal to negative gt plus v0 dt. Integrate both sides, and you get the y is equal to negative g over 2t squared plus v0t plus c2. And now we'll use that second boundary condition to find c2, the one that says when time is equal to 0, y is equal to y0. And so this says y0 is equal to negative g over 2 times 0 squared plus v0 times 0 plus c2. So c2 is equal to y sub 0. Now update. And you get that y as a function of time is equal to negative, I'll write it as negative 1/2 gt squared plus v0t plus y0. And that's, the other equation that you're familiar with from Physics 1 for a free fall problem. Any questions about either of those steps? Okay, it's definitely easier in the case where your only non-trivial function is t. But in dynamics, problems like that come up pretty often. It gets a little more complicated if you have to integrate both sides. You have to use logs a lot of times. Okay, so how are differential equations going to come up in this class? Well, the first way is that the velocity is equal to the time derivative of the position. Or you can write that as d dt of the position vector. The second way is that the acceleration is the time derivative of the velocity, or in other words, d dt of the velocity. And these are all definitions. I guess I'll give it this definition thing, like that can never be false, okay? The third one is the angular acceleration vector. Remember angular acceleration from Physics 1? In Physics 1, I don't think it probably wasn't a major point of emphasis that the angular acceleration is a vector, but it is. In 2 dimensions, it's just always a vector parallel to the z-axis. But this is defined as the time derivative of the angular velocity. Or in other words, d dt of the angular velocity. There's a couple other derivative relationships that'll come up later on, but these are the ones that I want you to always try to keep in the front of your brain, okay? These are going to come up all the time. Okay, let's try one. So let's say we have the example dq ds is equal to s squared over q. And we'll do this for s and q positive. So for the boundary condition, let's say Q is -4 when S is 2. Okay, so we want to solve this differential equation. So let's first just get our bearings together, and then I'll give you a little time to sort of think through this. Is this a partial or an ordinary differential equation? Ordinary. Everything that we can do in this class is ordinary. So if I give you a partial differential equation, that's actually what you're hoping for, because then you just write on it. We don't do those, you know. And then what's the independent variable? Yep. And what's the dependent variable? I didn't really hear that, but I'm going to assume that you said Q. Okay, so what we're trying to find is Q as a function of S. Okay, so take a couple minutes and see if you can find this solution, okay? Feel free to talk to each other as you go, compare steps as you go. Feel free to ask me questions. It's not like a test or anything, it's just a chance for a little practice while everyone's here. And then I'll go through it and you can sort of check your steps and make sure you're thinking about it right. Just finish before class ends. And when we do this, I would just recommend, check to see if you did it the same way I did. If so, great. If not, that tells you the step where you misunderstood something. Maybe it was just a dumb mistake or whatever, but it's just a way to sort of zero in on any places where you have misunderstandings. Okay, so we have Q dq is equal to S squared ds. So integrate both sides. Q squared over 2 is equal to S cubed over 3 plus C. Now we can use the boundary condition. And it says that Q is equal to 4 when S is equal to 2. So we have 4 squared over 2 is equal to 2 cubed over 3 plus C. So that says 8 minus 8/3 is equal to C. So that is equal to 16/3. Now update the function and you get Q squared over 2 is equal to S cubed over 3 plus 16/3. And now it's just a matter of expressing that in a function form. So x squared is equal to 2s cubed over 3 plus 32/3. So that's 2s cubed plus 32 over 3. Take the square root. We're dealing with positive Q and positive S, so we'll take the positive answer. Any questions about that? Okay, that's it. Long weekend, woo!